Hi guys, welcome to Vedant Education. So I have one more problem for you. This is from optical fibers. So this I picked from GATE 2015 question paper. So, so this is the question. So light from free space is incident at an angle theta I to the normal of the facet of a step index large core optical fiber. The core and cladding refractive indices are N1 equal to 1.5 and N2 equal to 1.4 respectively. The maximum value of theta I for which the incident light will be guided in the core of the fiber is. So this question is quite nice and it's one of my favorite questions. So this is quite easy to solve if you know about the total internal reflection, critical angle, and Snell's law. So that's it. You just need three basic formulas, and then you need to apply the right technique to get the answer. So optical fiber has a higher refractive index core surrounded by a lower refractive index cladding. So let me draw that out. So let me draw the optical fiber here. So it's basically the same thing which they have given in the question. So here is the core of the optical fiber, and this is the cladding. So this is the cladding. So let's say the core has the refractive index of N1, which is given in the question, which is 1.5, and N2 is 1.4. So note that the optical fiber always has a higher refractive index core, otherwise the light will not be guided. That's because I will tell that in a moment. That's because of the total internal reflection. So what you have to find is the maximum angle for which the maximum angle of the light which is incident on the optical fiber, for which the light is guided inside the optical fiber. So the basic principle of optical fiber light guidance is that the light which is incident on the core has to undergo total internal reflection. So let me draw that. So if this is the normal, so the light which is coming here, let's say that it is refracted due to this glass here. So then it goes like this, and then it hits the optical fiber interface between the core and the cladding. Now this light, in order to be guided, has to reflect from this surface. For that reflection to happen, this light should be greater than the critical angle. So this angle should be greater than the critical angle, then only it will be reflected again. So that's how the guidance principle is there in optical fiber. So if let's say that this is not going to hit it below the critical angle. So if the light is coming from this end, so let's say this is coming here, now it's refracted and it's not the critical angle, it's above the critical angle, and this light is lost. So it is not guided anymore. So this is the basic principle on which all the optical fibers work, and all your mobiles and other internet is working on the principle of light guidance inside the optical fiber. So what we have to find is the maximum angle at which, if we hit the core, it is guided inside the optical fiber. So this is quite easy to formulate. So let me formulate the problem. So here we have the core surface, and let's say this is the cladding. And now let me draw a normal here and a incident light. This is the maximum incident angle for which it is guided. So for the maximum incident light which is guided, the angle at which it is refracted has to be the critical angle. So at critical angle, what happens is, at critical angle, the light in the second medium is grazing the surface between these two, so the light will go at 90. Okay, so So this is the formulation. So let's first apply, this is N1 and this is N2, and let's first apply the Snell's law in this point. So when I apply Snell's law here, it says that, so let me just write it here. So for the Snell's law, what you can expect from this point here is that N1 sine theta c is equal to N2 sine. So since it's the angle at critical angle, it's grazing the surface, the angle the refracted angle in this medium, which is N2, is 90. So this is 90. So sine of 90, which is 1. So N1, we know that N1 is 1.5 sine theta c is equal to N2 is 1.4, and this is just 1. So from this we know that we can calculate theta c, which is the critical angle. So I will calculate this angle in my calculator. So theta c becomes 46.04 degrees. So we know that critical angle is 46.04 degrees. Now we know this angle, so we can calculate this angle, which is the theta r from the incident light. So theta r is just theta r is equal to 90 minus theta c, because this is at right angles. So that will become 43.95 degrees. So the theta r here is 43.95 degrees. Now let's apply the Snell's law at this point, at the incident point. So once I write that down, so I will just write it down here. So N1, which is here, this is the free space, so it's just 1. So N0 sine theta I equal to 1.5, which is this, which is the core refractive index, which is N1, 1.5 sine of theta r. And we know what is theta r, and we know what is N0, this is 1, and we know all the other values here. So theta I, we can calculate the theta I from here. So theta I equal to 76.32 degrees. So if the angle of incidence on this optical fiber is below 76.32, which is this one, if it's below 76.32, then the light will be guided inside the optical fiber. If it's above this value, then the light is just out, it's going out. Then we know that for the 76.32 degrees, not just an angle, it's a cone of angle, so it can accept all the light which is coming within this cone, and this cone has a angle which is half angle of 76.32 degrees. So this is one of the most important questions that often come in GATE, and it's really useful to know this method of solving for the maximum angle, maximum cone for which it's accepting the light. So we can also calculate Na from this. Na is just N1 square, N1 square minus N2 square, and we can calculate this value also. So we should remember both these formulas and the Snell's law to apply here in the right way to solve this problem, and it comes often in GATE. Thanks for the watching, guys, and please subscribe to our channel and click the bell button. Thank you.